Hey everyone, welcome back to another lesson of AP Precalc. This is lesson 2.3. Let's get right into it. All right, so here's a bell ringer for today. Pause the video if you haven't done this already, because I'm about to go over the answer. So we have here a table that gives the values of f of x at selected values of x. Which of the following best models this function, linear, quadratic, or exponential? Give a reason for your answer based on the change in outputs, the change in inputs, and then the actual values in the table. So this here, if we take a look, we see 50 to 25, 25 to 5, 5 to 1. So it's decreasing really quickly. So this is probably going to be exponential. And then here we're multiplying, we're really just dividing by 5. So here we're multiplying by 1/5. And we can see that pattern continues for all of those. And so I would say for my answer, over equally spaced inputs, and then I want to talk about the outputs. So for an exponential function, the output values change proportionately by a factor of, and then this should be 1/5. There. So I want to see over equally spaced inputs. I want to see how the output values change proportionately, and then I want to see by a factor of 1/5. Those are the three things I will be looking for in your answer on a potential test or quiz. All right, and now today we're going to be really looking in exponential functions. And so these are some of the most important functions in the real world. So why do they matter? Because they appear in multiple different places, maybe even some that you wouldn't expect, like how to potentially invest your NIL money with interest, how you can use an exponential function to also model how many followers will you gain when you blow up on TikTok, or how to predict the impact of COVID-19 maybe in a month span given some past historical data. So all three of these are really good examples of where exponential functions could be used or seen in the real world.
Cause we the big three, don't need a big speech. We made the biggest impact, check the spreadsheet.
And so these are the big three functions. These functions are most commonly seen on the SAT and the ACT and the AP exam. So you really want to get familiar with it. Obviously, we've worked with linear and quadratic functions thus far. I'm sure you've seen exponential functions in Algebra 1 or Algebra 2, but now that's what this unit is about, where we really dive deeper into those exponential functions and look more into those. And so for example 1, sketch the graph of each function, plot at least 3 points, and then find your y-intercept. So here, if we plug in -1 to this function, 2 times 3 to the negative first, anything to the negative first is just, this is 2 times 1 over 3. So our y value here should be 2/3. At 0, this should be 2. And then at 1, this should be 6. And so if we plot this, -1, 2/3 would be around there. 0, 2 would be right here. And then 1, 6 would be right here. And so as best I can on this computer, that's how I would model that exponential function for 2 times 3 to the power of x. All right, now we have 2 times 1/3 to the power of x. So if we do -1, 2 times 1/3 to the negative first, this flips the fraction. So this is technically 2 times 3 over 1, which is just 2 times 3, which is 6. So that's our output there. If you plug in 0, you should get 2. And then if we plug in 1, this is 2 times 1 over 3, which is just 2/3. And so that should be our answer there. And so notice how when you go from 3 to 1/3, it kind of reflects over the y-axis, right? And so this should be -1, 6, right there, 0, 2, and then 1, 2/3 right there. And so as best I can, this is how I would graph that exponential function like so. All right, so now that we kind of looked at a few exponential functions, let's look at a few key characteristics. So all exponential functions will have the form a times b to the power of x, where b is going to be bigger than 0, and you cannot have a equal 0, right? If you have 0 times b to the x, that's just equal to 0. That's no fun. Or you cannot have b be 1, because if you have a times 1 to the power of any number, this is just going to be a. That's going to be just a flat line. That's also no fun. And then if you have b as a negative number, you have a times maybe like negative 2 to the power of x. I know we experimented with some negative common ratios in lesson 2.1. However, here we don't really want to see oscillating exponential functions. So we don't want to see an exponential function look like bounce up and down. So we just don't have b be a negative number. And so b is always positive here. A will always represent the initial amount, while b will always represent the base or common ratio. So those two represent b. And now the two different types of exponential functions you will see is either exponential growth. This is where a is assumed to be positive. The same with exponential decay. A will be positive. So both of these, a is positive. However, for exponential growth, b, your number that you keep multiplying by, is going to be greater than 1. So for example, if you have a number, let's say a is 2, and then you keep tripling it, right? 3 is greater than 1, you're going to keep increasing it. And that's why it grows as you go from left to right. For exponential decay, a still is positive, but b is less than 1 but greater than 0. Remember, b can't be negative from this restriction here. And so this is like if we have a number 2 and you keep multiplying it by 1/2, you keep cutting it down, and so you're going to be decreasing as you go from left to right. And that's how we get that general shape of an exponential decay graph. And so quick, how would you describe the characteristics in this exponential function? And so let's listen to my good friend Young Jock and hear how he would have answered this question.
It's going down. Meet me in the mall. It's going down.
Okay, so he said it was going down. It's not super descriptive, so take a minute in your notes and see if you can fill in the blanks with the statements about that exponential function that looked like that. And so this is the answers. So here are some things that you could have said that would have been way more descriptive than what Young Jock said. And so, for example, it's exponential decay, right? It's going down. It has an initial value of a positive number. Its base or common ratio has a value between 0 and 1. That's true with all exponential decay functions. It's always decreasing, right? It's always just going down. It's always concave up, so part of that upwards U shape. There's no local mins or maxes, right? Because it's never going to go from decreasing to increasing. So it will only go down. So there's no local minimum and also no local maximum. There are also no points of inflection. And these are true with all exponential graphs. We'll talk about that more later. And then as x increases without bounds, the y values will approach 0, right? If we take a look at that graph, as you go to the right, this is going to get closer and closer to 0, but never touch it. And then as x decreases without bounds, the graph will approach infinity, right? As you go to the left forever, this is going to shoot up and go to positive infinity. And so now let's look at some key characteristics of exponential functions. The first one is increasing versus decreasing. So depending on if it's like growth or decay or anything like that, exponential functions are always increasing or always decreasing. They will never switch from one to the other, so they will never have any relative or local extrema, right? Because you get local extrema when you go from decreasing to increasing. That's where you get local extrema, like a local min there. However, exponential functions are just decreasing, so no local extrema will be produced from them. Next, we have concave up versus concave down. They will only be concave up or only be concave down, depending on the function. So for example, exponential growth and exponential decay are an example of concave up functions. They both have an upwards U shape there. And because they don't switch concavity, they have no points of inflection, right? There's no peaks and valleys to find a point of inflection between. So no points of inflections will exist on exponential functions. And behavior. So as the input values either increase or decrease without bound, another way of saying that is for any exponential function, as you go to the left or the right forever, either three things will happen. It's either going to increase forever, you could see it where it decreases forever, like this, or it's going to approach 0, right? So it's going to get closer and closer to that value of 0 there. So these are the limit statements. These should be pluses or minuses. But as the limit as x approaches positive or negative infinity of those exponential functions will either be one of three things: positive infinity, negative infinity, or 0 there. All right. So what happens when a is negative? When a is negative or just less than 0, the graph is, remember, flipped across the x-axis. It's a vertical reflection. We talked about that in 1.12 with transformations. And so while the function is still exponential, it's no longer considered exponential growth or decay. So for example, if we have 2 times 3 to the power of x, that's going to look like this function, an exponential growth. But then let's say that you add a negative sign, it's going to flip it, and that's going to be the new graph. Likewise, if we have 2 to the power of 1/3 x, that's going to be an exponential decay function, so like this. And now let's say you add a minus sign in front, that's going to flip it, and this is going to be the new graph of that exponential function there. So just be cognizant and cautious of if a is negative, then you just flip it over the x-axis. So how do we determine what the graph looks like? Pretty easy, like I just showed you. Ignore any negative signs if there are one, and then graph it as if it was exponential growth or decay, assuming a is positive, right? So just like forget a is even negative if it is negative. Sometimes it may not be negative. And so it should either be growth or decay. Then if a is negative, you flip it over the x-axis and you're done, right? Pretty easy. And so that is how we are going to graph these functions. And so classify each of the following as either exponential growth or decay. Notice how none of our a values here are negative, which means that they will fall under growth or decay because a is positive and it's an exponential. So here, our base, our b, is bigger than 1, so this is going to be growth. Here, this is less than 1, right? 1/2 is smaller than 1, so this is going to be decay. And then here, even though it's a fraction, this is going to be bigger than 1, right? 1 and 0.5, or 3/2, is bigger than 1, so this would be exponential growth, right? Example 4, match the following exponential equations to their respective graphs. So here, let's knock out the exponential growth and decay. So that's going to be 2 and 3. This has a base that is less than 1, so this is going to be exponential decay. So it should look like this, which matches D. So D should be number 3. 2 should be A, because this is going to be exponential growth. So 2 is A here. Now if we take a look at 1, right? If we ignore the negative sign, this is just 4 times 3 to the power of x, which is exponential growth. But because there is a negative sign, we flip it, and this matches up with b, so 1 should be b there. And then by process of elimination, this, if we ignore the negative sign, this just becomes exponential decay, and then with that negative 4 out there, you're going to flip it, and this matches up with c, so it does check out. That should be your answer for example number 4. All right, example number 5. Write the limit statements for the end behavior of the exponential function. So this should be If we write our left-hand limit, this is approaching 0, and our right hand, this is going to positive infinity. So the limit as x approaches negative infinity for f of x equals 0, and then the limit as x approaches positive infinity for f of x equals positive infinity. This should be the limit as x approaches negative infinity for h of x equals, and then this is going down forever, so negative infinity. And then the limit as x approaches positive infinity for h of x, this is approaching 0. And then here, if we graph this base b is smaller than 1, so it's going to be exponential decay. So now it's pretty easy to write our limit statements. The limit as x approaches negative infinity of g of x equals positive infinity, right? As we go to the left, this is going to shoot up. And then the limit as x approaches positive infinity of g of x, this should be 0. So those would be our 6 limit statements there. For example 6, for each of the following, circle if the exponential function is increasing or decreasing and concave up or concave down. So this is an upwards U shape and it's going down, so it's concave up and decreasing. This is a downwards U shape and it's going down, so concave down and decreasing. And then this function right here is an example of exponential growth, so it's concave up and increasing. So those should be our 6 answers there. And then finally, example number 7, let f of x equals 3 to the power of x. Which of the following statements about the graph of f is correct? So this is 1 times 3 to the x. You can assume a 1 if it's not stated. This is an example of exponential growth. And so this function is definitely increasing, right? So we can eliminate c and d because that says decreasing. And then here it says at an increasing or decreasing rate. That's going to be talking about the concavity. So what we want to do here is this is concave up, so the rate of change should also be increasing. So A should be our correct answer for example 7. If you have any questions, please come see me in office hours, and I will see you guys later. Thanks.